In this lecture, I will discuss about the plastic analysis of steel structures. Introduction. Although the term plastic analysis and design normally apply to such structures for steel structures within the yield flow region, means the plastic analysis is made for steel structures. Okay, here why? Because in steel structures yielding of steel is present. Okay, here is a stress strain curve of yield material of steel material. Okay, here from A to B, that is the elastic region. From B to C, that is a yield points. From C to D, that is a plastic strain flow. From D to E, that is strain hardening. In strain hardening, steel again start taking the load, and from E to F, that is a failure. Okay, so however, the idea may also be applied to reinforced concrete structures. Okay, this plastic analysis we can also enhance for the reinforced concrete structures which are designed at ultimate loads near yielding of reinforcement. Okay, due to the yielding of reinforcement bars in reinforced concrete structures, we can extend the idea of plastic analysis in concrete structures. Okay, now next, the true stress strain curve for a low grade structural steel is shown in figure 1. Okay, here in this figure 1, the basic stress strain curve of steel material is shown. Okay, but for plastic analysis, while an idealized one is shown in figure 2, here in figure 2, idealized stress strain curve is shown, which forms the basis of plastic analysis and designs. Means for the plastic of analysis and design, we use this bilinear curve, elastic and plastic curve. Okay, for the plastic analysis of structures. Okay, this is a simplified form of this stress strain curve of steel material. Okay, so that from A to B, that is a plastic, and from B or C comma C to D, that is a plastic region. Advantages of plastic analysis. Okay, why we perform the plastic analysis? Ultimate loads means after performing the plastic analysis, we get ultimate loads where the failure will occur. Ultimate loads for structures and their component may be determined. Means we can understand the behavior of structure in term of failure, from where the failure start in the structure when the loading applied on the structure or when loading exceed the capacity of the member. Sequence and final mode of failure may be known and the capacity at relevant stages may be determined. Mean at relevant stages near to failure, we can determine what will be the capacity of the member. We can get by using the plastic analysis. Before performing plastic analysis, we make assumptions. Okay, here are the assumptions. The material is homogeneous and isotropic. Means the material is homogeneous. There is no composition. That is how the whole material is the steel material. Member cross section is symmetrical about the axis at right angles to the axis of bending. Means okay, now the member cross section is symmetrical about the neutral axis. Okay, at right angles about the neutral axis, the member cross section is symmetrical. Cross section which were plane before bending, when we try to bend any beam, then their fiber go some in the curvy shape. So we make the assumption that cross section which were plane before bending remain plane after bending. Fourth, the value of modulus of elasticity of material remains the same in tension as well as in the compression. Okay, when we see the stress profile, bending stress profile, then the elastic modulus of elasticity will remain same in the tension region and in the compression region. Fifth, effects of temperature, fatigue, shear, and axial force are neglected in the plastic analysis. 6. Idealized bilinear stress strain curve will be applied. Means for the plastic analysis we will use this uh, stress strain curve, elastic plastic curve we will use. Okay, number of plastic hinges. Before number of plastic hinges, I will describe what is plastic hinge. Okay, here is simply supported beam. Okay, here is the bending moment when we apply the load on the simply supported beam. Okay, when we apply the UDL on the simply supported beam, that is the bending moment curve. At the support there is zero moment. Okay, at the center there is a maximum moment. Okay, when the load, for example, if there is actual steel beam and on which the loading is applied, then if the loading exceed the moment capacity, okay, if the the applied loading exceed the this steel beam, if the applied load which is acting on this beam is exceed the maximum moment capacity of this beam, then the beam definitely will go for failure. Okay, now failure will start. Okay, definitely the failure will start at the maximum moment location. Okay, failure will start at the center of the beam. When the failure will start, okay, we know the stress strain curve of steel. Okay, when the failure will start, definitely the failure at the failure the yield point will come. When the yield point will come, okay, then at this section, this at the center of this section of the steel, the beam will loses its moment capacity. Okay, beams is going to fail, means beam will no more take the moment, so it means at the center the beam loses its moment capacity. Okay, because beams is going to under failure. When yielding will occur, okay, at the center due to exceeding of applied loads, and as a result of applied loads there will be more bending moment, uh, uh, bending moment as compared to the capacity of this beam, then yielding will occur at the center of the beam. This point where yielding will occur, that is called plastic hinge. Okay, the yield point that will in the plastic range, because we use a simplified bilinear curve. Now this is a plastic range, so that's why this point is called plastic hinge. Okay, now let's see for another beam. Okay, here is fixed ended beam. Okay, I have applied UDL on the fixed ended beam. The bending moment curve of fixed ended beam here. At this spot, the moment value is omega L square by 12. Okay, on the left side also omega L square by 12, and at the center that is omega L square by 24. Okay, means at the center there is half moment as compared to spot. Omega L square by 2 is bigger value, omega L square by 24 that is a smaller value. So when the loading exceed against the moment capacity of the steel beam, okay, this beam, then first failure will start at the spot, because the due to the load more moment is coming at the spot, omega L square by 12, omega L square by 12. So it means when due to the exceeding of loading, okay, against the capacity of this beam, then for first yield point will form at this location and at this location. Okay, so yielding will occur at this point and this point. Okay, then when yield, it means now these ports are no more ready to take the moments because they loses its capacity. Before exceeding of the loads, this beam taking the load moment of omega L square by 12 at this port and this port due to the fixity. But due to the exceedance of load in the beam, now the beam can no more, means do not take any further movement because it is yielding, it has lose its capacity of movement. Now where this moment will go, this moment will transfer at the center. Okay, if you sum up omega L square by 12 and omega L square by 24, okay, and you will get the total moment that will be omega L square by 12. Now this after yielding of the moments of these spots, okay, yielding of spots, this new beam will become like this. Okay, at this spot the beam loses its capacity to resist the moment. Now all the moment from the spots transfer to the center. Okay, now the beam will behave like a simply spotted beam after yielding. Okay, now again at the center the moment will be omega L square by 8. Now after forming of the hinges, okay, this is converted into simply spotted beam. Beam will not still fail. Okay, means beam will not collapse. Okay, now the load is keep on increasing until the moment reaches to omega L square by 12. Then again a plastic hinge will form at the center of this beam. Okay, now this beam do not have the capacity to resist the moment at the center also. Now this beam will collapse. Okay, that's the phenomena of fixed ended beam. Means first hinges, plastic hinges will form at the spots, then the moment the moment which is resisted by the spots will be released and the moment will transfer to the center. Okay, how it will act as a simply spotted beam. The center moment will become omega L square by 8. Okay, so then the load will keep on increasing until the load value reaches to omega L square by 8. Then again the plastic hinge will form at the center of this beam, then the beam will fail. Okay, here failure, how failure will occur here, simply spotted beam. Okay, that is perfect, okay, that is stable. This beam will fail if the yielding will occur at center of the beam. Now the beam will collapse, okay. Similarly, I have shown in the fixed-ended beam, okay, failure will occur. First yield point at the spots will form, that will act as a hinge, but the beam will still not fail, okay. Beam fail when a hinge will form at the center. Now the whole beam do not have capacity to resist the movement, okay. Now the beam will fail, okay. No stable elements, okay, due to the hinge formation at the center, so the beam will collapse, okay. Similarly, take another example. Here, that is a propped cantilever beam. One side, that is a fixed, other side is a roller or hinge, that is a propped cantilever beam. The moment diagram of this beam I am showing on this beam here, okay. Now in the prop cantilever beam, one hinge will form at this point and one hinge will form at this point, okay. Now the beam will fail, okay. The first hinge will form where the movement is maximum, okay. Then the second hinge form where the movement is uh, uh, when there is movement is minimum. So when these two hinges will form, then the beam will fail. That is the theory of plastic analysis. Okay, you may observe that is the determinate structure, that is indeterminate structure, that is again indeterminate structure, okay. Yeah, this indeterminate structure need only one hinge, okay, one hinge for collapse, okay. Here prop cantilever beam, in this beam you can see the degree of indeterminacy is 1, degree of indeterminacy is 1. So how many hinges are needed? That is degree of indeterminacy plus 1, n plus 1, okay. For the failure of this beam means how many hinges are needed. The degree of indeterminacy, in this case degree of indeterminacy is 1 plus 1, means 2 hinges are needed for the failure. In the fixed ended beam, okay, the degree of indeterminacy is 2, okay. The formula is n plus 1, n plus 1. So the degree of indeterminacy is 2 plus 1. So total 3 number of hinges are needed for the failure. The proper word is used, failure mechanism, okay. The failure mechanism will form if 3 hinges will form in the fixed ended beam, okay. If this hinge and this hinge form, left and right hinges are only formed, the beam will be still stable, it will take the load, okay, it will not go for the failure. So means 3 hinges are needed for the failure mechanism.